All right, we are live.
Welcome, lads and ladettes, to Aether Roundtable number 99. Seeing Red, continued. Brought to you by Nicki Minaj
Shout out to Nicki
and
Minaj.
Alan.
All right, so we're going to pick up where we left off 1 year and 33 days ago, give or take a third. And we're going to read a chapter of Halton Arp's book, Seeing Red. But before we do that, I'm going to give a little recap on what we've previously read, and then we're going to watch a video that gives some evidence that verifies or that supports what ARP was putting forward in terms of galaxies and quasars having a physical connection via filament. So what we've been reading is Halton Arp, who was a PhD astronomer, and he was making observations of quasars and galaxies, and he was at specific wavelengths, and he was noting that when you look at them under certain X-ray and UV spectrums, you'll see that the galaxies and quasars are physically connected by a jet stream of physical material. And that would be impossible under the current cosmological paradigm because they assert that the amount of spectral redshift that they get when they analyze the light indicates a velocity, which indicates a distance traveled, which means that the distance between a highly redshifted quasar and a galaxy that's seemingly nearby, optically angularly to one another, they would argue that they're actually like billions and billions and billions of light years apart. And they're determining that based off of how they're looking at redshift. So everything's moving away from one another. That's how they keep the cosmological paradigm alive, that everything came from a big bang and everything is going in all directions. There's no preferred anything like that. So that's how they're getting their interpretation. So what he's observing here is the exact opposite, where the quasar, because in the current cosmological paradigm, the quasar is an old object. It was there first, and then the galaxies came. So that's why the spectrum shift discrepancy gives them a different distance apart because of the magnitude of the shift. Now, what ARP observed, you could interpret it because they're connected, is that the galaxy is ejecting through a jet stream, material and energy, and that is outputting these quasars. That's creating these little quasars, and then those quasars would go on to become their own galaxies. So he's saying that there's an intrinsic redshift due to new matter creation. And now, I don't necessarily agree with that interpretation, but that's what he was putting forward in a way that would make sense in terms of how these could be physically connected and not be, this vast distance apart that's like unfathomable. You can't even fathom multiple billions of light years away. It doesn't even make sense, but you can calculate it out, look at this huge number, and that's what they would say their distance apart is. But none of that is supported if they're actually physically connected. Right? That would be impossible to explain. So he goes through a whole bunch of these observations. So this is a repeating theme now where he's showing different galaxies when you're looking at their the axis of their ejection center. I forget what it's called, the galactic center. That's ejecting their energy from it. That is intersecting with quasars, like indicating that it's being ejected from it. So there's some relationship there that is meaningful, but in the mainstream paradigm, it will not be. It can't be acknowledged. They act like it's complete. It's just happenstance. And there's been a few instances since that were covered in the book where ARP had put forward, had made this connection of the filaments under a certain spectrum. And then years later, it would be co-opted as, oh, look, now that we have a relativistic explanation for it, we'll acknowledge this filament and, all this kind of stuff. So you see the kind of pick and choose with how they want to interpret the cosmological data. So this is a good insight on the highest levels of academia, because all of, physics and astronomy, geophysics is dependent on astrophysics, because when you go to look at any geophysics book, what you'll find is, hey, we looked at this star, we know how its inner core works based on its spectral readings, and that's how we determine how the Earth works. That's how they backwards derive it from what they're interpreting in the sky. So we'll go ahead now and start with the the Thunderbolts project, where the creator of the channel, See the Pattern, is going to do a little Prezi on this filament connection that I was going over, and then we'll go ahead and read the next chapter of the book from where we left off. So there's nine chapters total there, and we made it up to 6. Very cool. All right, I'm going to let this play out. Let me know if the audio is good.
A new study recently revealed the best ever.
Oh wait, I don't even have audio. Hold on.
Yeah, no audio.
It's great.
Testing 1 2. Good.
If I had Linux, could I hear it? Is that what you're saying?
Evidence by far of the cosmic
Yeah, there
filament.
we go.
Oh, there we go. You're gonna have to full screen that.
A new study recently revealed the best evidence by far of the cosmic filaments that connect ancient galaxies to what is called the cosmic web. Mainstream scientists think these filaments in the cosmic web are created by the elusive dark matter, which clumps together into filaments and causes normal matter to clump along these. Now, so far we have not been able to detect any of this supposed dark matter. The more we look for this dark matter, the more normal matter we find, often in the form of plasma. For the first time, scientists have spotted what they term a pipeline gas filament feeding an enormous galaxy that they believe formed when the universe was only 2.5 billion years old. This discovery seems to support a long-standing model that suggests star-forming material is delivered to huge galaxies via these cosmic filaments. They have previously detected these filaments connecting to galaxies, but those were not able to capture detailed chemical information of this stream. Fu and his colleagues were able to identify the chemical signature of the gas streaming into the galaxy, thanks to a very rare and fortuitous alignment of some quasars. They believe these quasars are situated far behind the galaxy and could be used as a light source to help see the details in the gas stream more clearly. They were able to probe the abundance of chemicals in the filament using the light from the quasar. These showed that the stream lacked heavy elements such as aluminium, carbon, iron, and magnesium. This implied that the gas had to be flowing in towards the galaxy, as if the gas was flowing out of the galaxy, it would have been enriched with heavy elements which are produced by the stars in the galaxy. These filaments seem to be the only way that this cold gas could get pumped into the galaxy without being disrupted by the hot atmospheric surroundings of the galaxy. They believe that this is a process that is important in understanding how these massive galaxies formed in the early universe. Now let's just take a step back here, as there are many aspects to this report which would lead to a very different conclusion. We will start with the fact that this bulk of work focuses on what they consider massive starburst galaxies at high redshifts in the vicinity of background quasars. Add into this the fact that they detect gas around these quasars that appears to connect them to the galaxy itself. Many of you will be familiar with the brilliant Halton Arp and his extensive work looking at exactly these scenarios. He found a clear correlation to the proximity of quasars and a host galaxy, and speculated that these quasars were ejected from the host galaxies and would continue outwards from these and slowly develop into a companion galaxy later on. He also saw very strong evidence of this ejection process occurring in an X pattern through the center of the galaxy. Here are some examples from the many images that Halton examined. Let's just take another look at this galaxy. We can clearly see the quasars that they identify seem to be strung out below the galaxy. Not in a perfectly straight line, but more an arc shape. Halton felt that this arc curve may be caused by the galaxy rotating by up to a quarter of a turn. We also see a companion galaxy off on the other axis, situated some distance from the host galaxy. Halton was also able to find examples of quasars that were clearly embedded in gas material that connected all the way back to the host galaxy. This is exactly what we are seeing here as well. When Halton made these discoveries, they were ignored as the redshift of the quasars would place them much further back than the host galaxy, despite the connection via the gas cloud. The redshift of these objects is not solely related to the recessional velocity, and hence their distance from us. Halton viewed that the redshift was instead an intrinsic component of the object, that as the object aged would reduce. So quasars are initially born as high redshift objects and then slowly reduce their redshift. Once they evolve into a companion galaxy, their redshift would be almost the same as the host galaxy. The important point was that the redshift of the quasars was always an offset of the original host galaxy. And when we look at the redshift of the object, we do indeed see that the redshift of the quasar does reduce as you move further out. So the first quasar would have a 0.242 higher redshift than the host galaxy, and the second quasar only 0.075, so again as we're moving further out this is reducing. If we examine the two companion galaxies that they have identified, again here we see a much lower value for the redshift, as these, in Halton's view, would be more mature. Now these steps also fit quite closely with the quantization that Halton Arp saw for these types of objects as they move further out from the host galaxy. This galaxy also reminds me of NGC 3067 and the quasar 3C232, which Halton Arp looked at. Here there was a quasar embedded in a hydrogen filament. Astronomers claimed that the quasar had to be situated behind the filament and could not be embedded within it. The argument was that the filament at the same redshift of the galaxy absorbed continuum light from the quasar, but did not show excited optical emission lines, proving that the quasar was much further back than the hydrogen filament. Halton, however, pointed out that in order to get to this conclusion, they needed to make a short extrapolation. The photons needed to ionize the hydrogen in the filament and make it fluoresce were at a shorter wavelength than those in the spectrum. The actual amount needs to be determined by the amount of hydrogen at redshift intermediates between the quasar and the hydrogen filament, the degree to which the filament was composed of small dense clouds, and the relative beaming angle between the ultraviolet and radio wavelengths of the quasar. These are all values they do not know, so they have to guess in order to derive their value. Now, one important point to realize is that they see...
No way! They inputted the exact numerical values that they needed to confirm that it was actually behind the filament and not embedded in it, dude. That's fantastic.
Ridiculous.
Some good science.
It's legendary. Dude, no wonder they had to keep this guy banned from observations, dude. He's just like, you have to assume everything to even assert mutual exclusivity, right? Dude, classic.
A direct link between these star-forming galaxies and the neutral gas reservoirs that may fuel the future star formation. Again, here we must consider the type of galaxy. These are considered to be active galaxies, and once more these are exactly the galaxies that Halton had identified. These types of galaxies often had quasars associated with them and companion galaxies. We know that these types of galaxies also output vast amounts of materials from massive jets that they produce. It was along these jets that Halton found many of the associated quasars. The material was not flowing inwards, but was flowing outwards in his view, forming a sort of umbilical cord back to the host galaxy. Another important point to realize is that if you accept the idea that redshift is largely an intrinsic component of the host object, then this too would apply to the galaxy. This immediately would mean that this too is not a distant massive old galaxy. Instead, it is a younger, more active one in the process of creating newer, younger galaxies through the emission of these quasars. The increased activity will also lead to more energy within the galaxy and hence a higher current density, leading to rapid star formation. They identify interesting absorption structures towards both quasars, which include variable metallicities and what the author sees as a filament structure which will eventually collapse to form a cluster of galaxies. This and the unexpectedly large covering factor that they have identified for the quasars is much easier to explain if you take the bold step to see that these quasars are instead embedded within the filament. Where they identify a filament structure which is associated with the quasar, this is actually the umbilical cord connecting the quasar back into the large filament extending from the host galaxy. Galaxies undergo a life cycle, which includes the ejection of material,
The galactic umbilical cord.
which forms quasars, which eventually forms companion galaxies. We see all these phases in this galaxy and its surroundings. We see clear evidence of the existence of filaments connecting to the galaxy. We see companion galaxies located along two of the axes of the galaxy, and most importantly we see two quasars embedded within the filament, and these have a delicate filament structure that connects them back into this filament. At some point, coincidences cease to exist. You must start to see the data in a new light. Halton Arp was a pioneer in this field. Our universe is electric and screams this at every possible opportunity. You just have to be willing to shake off the old paradigms to see it come to life.
Dude, well said. That was a great presentation with awesome visuals to really illustrate what was being put forward in the book that we were reading a year ago. It was awesome.
Clusters of galaxies. And imagine, look at all the stuff that they know just from
Dude.
looking up. Imagine what they'll know tomorrow, to quote Men in Black.
It's like, hey,
Called it a pipeline or a gas pipeline filament. Like, what the fuck? Sorry. Continue, my bad.
no, you're good. It's just really interesting that to even keep their randomized, uniformity, no connection, no purpose hypothesis, they had to assume like 9 parameters.
Insane.
That's crazy, dude. Like if you just have the freedom to do that, then like you can do anything. Like it's whatever you say it is, bro.
Isn't there a quote that says that exact thing about astrophysics? Like we can just say whatever we want. Doesn't matter.
Yeah, I think there is a direct quote from Guy McGuyerson.
Who's
Yeah, I
going to
think
prove
that
you wrong?
quote. Yeah, that quote's engraved on planet Nibiru, on the second echelon of the Pillar of Truth, or some shit like that. I'm just kidding. I don't know. I'm just making shit up like they did.
Could
All
be
right.
true though.
Well, we're gonna read this chapter of the old book here, and then we'll round it off for the night. So next week, I'm going to be doing a presentation to recap what we've learned in this book. So it's been awesome, and then I remember going through the story of like all the academic encounters this guy had, where he was like, "Hey, I have these pictures here, and they prove this thing," and everyone just ignored them. And then later, when they found a way to incorporate it in their cosmological model in a way that wasn't damning, they finally acknowledged the measurements, but didn't acknowledge ARP. Classic, dude. All right, so the cluster of galaxies, chapter 6. Are there other clusters of galaxies which look like the cluster at the center of our local supercluster, the Virgo cluster? Is the universe populated with more distant examples of such great clusters? Everyone believes there are many, and 4,073 of them are listed in the revised Northern and Southern Abell catalog. They were originally cataloged by George Abell and later Harold Corwin from the Wide Field Schmidt telescope photographs, and are defined as containing, in addition to the 2 brightest stars, at least 30 galaxies within a range of 2 magnitudes. The brightest galaxy in the cluster range from the little fainter to those in Virgo who are about M19th apparent magnitudes, and redshifts reach about Z equals 0.2. The M used to describe the brightness of the galaxies in the cluster is that about 1/10 of its brightness. Is about 1/10 of the brightness Galaxy clusters in Virgo. Figure 6.1a is taken from the X-ray map of the Virgo cluster, which is shown in figure 5.14 of the previous chapter. More identifications of objects, however, have been added. Of the most interest for this chapter are the 4 bright Abell clusters running down the spine of the Virgo cluster. They are shown in figure 6.1b with only their strongest X-rays contours around them. These 4 are bright X-ray sources, and they are the only Abell clusters identified as such within the framed area. It seems extremely unlikely that this is a chance arrangement. Moreover, there are individual features of the cluster which support their association with the Virgo cluster. My attention was first drawn to the cluster A1541 because the X-ray contours were extended in a direction away from M49. As figures 6.1 and 6.2 show, the contours also lie along the outer edge of the narrow opening cone of the ejected quasar from M49, which was shown in figure 5.6. The X-ray contours are rather clear in pointing to M49, but could this galaxy cluster at a redshift of Z times C equals 0.9 times 300,000 kilometers a second equals 20 kilometers a second, or 27,000 kilometers a second, be a member of the Virgo cluster at the given velocity of the shift corresponding to 863 kilometers a second. And then here we have our figures here, and all these are filaments that are interconnected to the parent galaxy there, your boy M49 down here. When the question is asked in this way, the answer is a surprising yes, because the quasars of a much higher redshift were previously shown to be members. But in another sense, the question is of a shocking impossibility. After all, the impressive version of the Hubble relation, which reached the galaxies of the faintest apparent magnitude and had a very small dispersion, was built up by sandage out of the galaxy cluster. Everyone, myself included, thinks intrinsically that the galaxy clusters, as galaxies like our own, are seen at great distances. The only recourse was to examine the picture further. It turns out that 3 of the 4 clusters running along the backbone of Virgo in figure 6.1b have redshifts of 0.9, 0.8, and 0.8. This would indicate that they were related in some way, but if they were distant, why would they fall along the central line of the cluster? Particularly, A1552 is a relatively large in its contour, but it seems to emerge from a bright X-ray region on the southwest side of the modeled and subtracted image of M87. I know from my plates with the 200-inch telescope that there is a double galaxy about 1 arc minute southwest of UGC 7652, which is aligned back towards the nucleus of M87 in a configuration very suggestive of ejection. That's hilarious. They just see it everywhere they go. And they're like, nope, it's not happening here, guys. They're not related at all. It is a much higher redshift than M87 and is probably connected with the cluster A1552. In a third cluster along the line of A1569, the contours appear aligned in a direction away from the Seyfert 1 galaxy IC3528. This appears to be the classic case of the low redshift being 660 kilometers a second. The SC galaxy NGC 4595, connected by a trail of X-ray emissions to a high redshifted Seyfert companion, where the redshift is equal to 0.046. The Seyfert then ejects a new X-ray in the opposite direction. One ejection coincides with the A1569 cluster at a redshift of 0.8. It is rewarding to inspect this configuration closely in figure 6.1a. Note also that the X-ray contours of A1569 point back to the Seyfert. Finally, the cluster A1553 lies closely on the line between M49 and M87. That line, we know, when extended south from M49, leads directly to the famous 3C273. And here we have our image here. Inside the dashed region are shown the catalog of quasars and high redshift objects. They appear in clusters around a very active Seyfert, NGC 5548. In the large pictured region, the brightest galaxy is, and the brightest BL lac are indicated. Okay. Which has a redshift of, let me go back a second. Let's see, these are the line that is that we know is extended southward from M49 leads directly to the famous 3C273, which has a redshift of Z equals 0.158. When we extend the line northward from M49, it leads to A1553, which has a redshift of 1.56 or 0.156, sorry. Is this the counter ejection from 3C? Is M87 instead an earlier ejection? People have sometimes said to me, if you're going to make extraordinary claims, you must provide extraordinary proof. Usually they exit smiling smugly, and I think dark thoughts like, no proof is extraordinary enough. But if something is true, then it always has the possibility that you can find some extraordinary proof. Okay. A connection with the Seyfert NGC 5548. At about the same time, around 1993, when H.C. Thomas showed me his observations of the bright BL lac object, I noticed a 36 arc minute south of the strong X-ray source with an apparent jet. This source turned out to be a very active Seyfert galaxy NGC 5548. Since the field had been included in the Einstein Laboratory Medium Sensitivity Survey, it was shown that there were 3 X-ray quasars within about 15 arc minutes of the Z equals 0.56 and Z equals 67 and 1.06. Also were cataloged were the quasars of 1.80 and 1.83, 1.87, and 2.31 nearby. Clearly as figure 6.3 shows, there was a connection of active objects in this small region of sky. Let's see, what was that within 15 arc minutes? That's pretty small. All right. But most important for the purpose of this chapter, the apparent X-ray jet emerging from the northeast direction of NGC 5548. With the help of Hans Christoph, I was able to obtain the IPC frame as shown here in 6.4. The, quote, jet is a visible, broadened, and centered about 8 arc minutes from the nucleus of NGC 5548. There appears to be a narrow break in the continuity of the X-ray emission between NGC 5548 and the X-ray object. Later, Radek and I were able to obtain a ROSAT exposure of the from the archives, and this is a slightly deeper, slightly lower energy range shown in figure 5.6, shown in addition to the elongation of the X-ray object towards NGC 5548, a narrow filament joining the two objects. And here we have our ROSAT, I guess, from the, figure 6.4, the Einstein Laboratory X-ray of NGC 5548 showing the strong jet-like emergence, which turns out to be a galaxy cluster with a redshift of Z equals 0.29. All right. The optical identification of this object or elongated X-ray emission is therefore crucial. On the Palomar-Schmidt sky survey, at this position, there is an extreme limit of the red and blue prints, what appears to be a faint elongated cluster of galaxies. This seems to be confirmed by the measurement of John Stock and others of the non-emission lines of galaxy at Z.29. Note the closeness of the major quasar with the redshift peak at Z equals 0.30. And consider if you broke it up into an 18th apparent magnitude quasar into 16 pieces, you would have fainter components of about M equals 21 magnitude. Because of this new evidence, the faint galaxy clusters are in fact ejected from the active galaxies. The cluster adjoining NGC 5548 becomes a crucial case for further investigation, high resolution, deep images with spectra with Hubble Space Telescope or large ground-based telescopes would seem to be the highest of priorities. So we got our diagrams here of some nice interconnected filaments linking everything together. A nice elongation bridging the galaxies and quasars together. Three X-ray clusters in a line. In a separate event about this time, I had happened to notice in an article in the European Southern Observatory, which pictured the distribution of galaxies in three adjacent Abel clusters. Figure 6.6 shows that these three clusters define approximately a straight line, but it also happens, as the figure shows, that a very bright, very active galaxy falls at about the terminus of that line. NGC 5253 is a well-known, exceptionally active starburst galaxy. It is also an active X-ray galaxy with a filament coming out of the south and splitting east and southwest, with at least three additional X-rays. With at least three additional X-ray sources leading over it into the line of the three Abel clusters in Figure 6.6. To show the three Abel clusters are bright in X-ray, in a list of the X-ray clusters ranked by apparent flux given by LaVey and others, these clusters rank number 26 and 29. About the same distance on the other side of NGC 5253, however, lies A3571, an exceptionally bright X-ray cluster, an apparent flux with which ranks fifth after such clusters as Virgo, Coma, and A2319. So the situation we are faced with is that these three clusters, two of which are strong X-ray sources, form a line which appears to originate at the bright starburst galaxy. This galaxy itself is an X-ray source with a jet and has X-ray material that appears to extend in the general direction of the line of clusters. In sum, we find that the galaxy NGC 5253, near the center of the broken line, angled at about 35 degrees, of usually bright X-ray clusters, bright X-ray clusters. It was natural at this point to look at the disposition of the Abel clusters over the wide area around NGC 5253 in order to appraise the possibility of the observed configuration occurring by chance. Okay. So we have figure 6.7. The Abel galaxy cluster with M equal to or brighter than 16.5 apparent magnitude are plotted over this apparent 30 by 30 degree region of the southern sky. Small boxes identify brightest galaxies with their apparent magnitudes and redshifts in kilometers per second. Contour lines of radio emissions from the giant radio galaxy Centaurus are shown, or Centaurus A. The dashed lines show the location of the galactic latitude, 20 degrees. Plot of the bright clusters of the North Centaurus A. Investigating the cluster population around NGC 5253 made it clear that it was necessary to plot the cluster positions over a wider and wider area in order to judge the average background density of clusters. Figure 6.7 is that result and shows the north of the 11.1 magnitude. NGC 5253 lies in the 8.5 magnitude M83, which has the suggested line of a cluster passing through it. And in fact, M83 may claim the strong X-ray cluster northeast of NGC 5253. It is a fascinating game to try to find the objects which belong to which bright galaxies in the crowded regions. Just south of the galaxy 5253 is an active radio galaxy, IC 42696, which is near some of the clusters with a redshift of z equals 0.011. IC 4296 is below the cutoff in this apparent magnitude for the plotting in figure 6.7, but other studies have indicated that it is a member of the line of galaxies associated with Centaurus A. See figure 5.5. Here, also published in this publication here. And, okay. The situation is that there are so many bright and active galaxies in Centaurus A, in the Centaurus A line, that it is difficult without further study to ascertain which cluster belongs to which galaxy. But overall, the results of figure 6.7 is even more stunningly clear, with the important and namely bright able cluster of galaxies in this large region of the sky are distributed in the same characteristic way as the bright and active galaxies that belong to Centaurus A. Figure 6.8, the enlargement of region around Centaurus A showing the able clusters with an M of 16.9 or greater. The smaller arrow indicates the direction of the strong radio and X-ray jets in the interior Centaurus. Since the higher redshift galaxies in the line of Centaurus A, of Cen A line are presumed to have originated in ejection from the giant active radio galaxies, the able clusters are so densely surrounding these second generation galaxies are implied to be the third generation ejecta in various directions, but still relatively close to their galaxies of origin. Cen A at the bottom of figure 6.7 with its outer radio isophotes sketched in resemble a flame with the sparks of the galaxy and cluster rising upward. If we ask whether there are any clusters directly associated with Cen A, we can consult a smaller field as shown in figure 6.8. There we see there are only 3 catalog clusters, and that they are all brighter than a magnitude of 16.9. 2 lie on the Cen A and 1 lie on the other side. 2 lie on one side of Cen A and the 1 on the other side. All 3 are seen in X-rays in the analysis of a 10 by 10 degree. A Rosat field, the direction of the innermost X-ray in the radio jets is indicated by the arrow. The disposition of the alignment of these 3 closest clusters would seem to unequivocally establish their primary ejection origin from Cen A. 2 further aspects of this should be noted about the clusters in this region around Cen A. First, the able clusters in 6.7, which have measured a redshift that falls in 2 distinct groups. There are 6 with a magnitude greater than 0.011 and 0.17, and 7 with a magnitude of 0.35 and 0.55. The segregation can also be seen with the Hubble diagram in figure 6.14. Redshift discretionized is typical of the galaxies with an intrinsic redshift is evidence of the distance related to the redshifts and is probably due to the episodic nature of the matter of the creation of matter events. So this is him giving his theory on the old matter creation there. Figure 6.9, the able cluster with M equal to or brighter than 17.2 in a region centered on Virgo A and its jets. The cluster of redshift of 0.078 in the northeast and 0.084 to the southwest were identified in figure 6.1 B as belonging to the Virgo cluster. Some symbol sizes proportional to magnitude and brightness. All right. Secondly, the most significant concentration cluster over the huge regions in figure 6.7 occur at the brightest able clusters as plotted. We see that in the following sections that the other active galaxies show a strong associations with the bright Abel clusters, but Cyn A is the closest of these systems and would be expected, or as would be expected, its associated Abel cluster with the brightest and most are the most brightest and most widely spread. The Abel cluster associated with Virgo A, which is M87. Proceeding from Cyn A to the next brightest radio galaxy in the sky, Virgo A, which is M87 there, we encounter another giant E galaxy in which the radio jet, X-ray jet, and now optical jet are coincident and define a precise ejection axis. Perhaps even more accurately than Cyn A, the numbers of bright E galaxies fall along these ejection directions from Vir A, defining the length of the sky at about 8 degrees, as shown in figures 5.3 and 5.4 in the previous chapter. In figure 6.9, all cataloged Abel clusters with a M brighter than 17.2 are plotted in the area of Vir A and the principal extension of its jet directions. It is clear from that diagram that the Abel cluster also defined the direction of the same ejection line. Note that the quasar/Seyfert PG 1211 plus 14.3 discussed in chapter 2 lies closely in this same line, closely along the same line. The brightest clusters indicated by the size of the plus symbol define the line best. 2 clusters along the line measured redshifts of 0.0484 and 0.079 indicate empirically that they are associated, even though quite far separated along the line. The fainter cluster in the northeast corner with a Z of 0.078 is Abel 1569, associated with the objects in the X-ray extension north-northeast of M87 shown in the map of figure 6.1. The Abel cluster region of Perseus A. In 1968, it was shown that essentially all bright radio galaxies had a smaller galaxy emerging from them. Per A is another very strong radio galaxy and is well known to have a straight line of galaxies proceeding almost due west from it. What is not well known is that the chain of galaxies ends on a very bright nearby galaxy, as shown in figure 6-10, shows the Abel clusters in a region with a magnitude greater than 17.4. It is clear that there is a straight line cluster connecting to per A with NGC 89.1. The 10th brightest SB galaxy in the northern sky declinations. NGC 89.1 is well known as a nearly edge disk on NGC 89.1 is well known as a nearly edge on a disk galaxy with consequently its major axis well defined in the sky. That direction is close to the east-west and is indicated by the arrow in figure 6.10. The reason this point is noted here is that although NGC 891 is not at present a particularly active galaxy, spirals do intermittently eject material, and the evidence favors the ejection along the minor axis. Of course, what we are seeing in figure 6.10 is the famous Perseus-Pisces chain of galaxies, Pisces. This narrow chain stretches about 90 degrees across the sky. The redshift of the galaxies characteristically range from about 4,000 to 6,000 kilometers a second. If this dispersion in the redshift were to be translated into a velocity, the filament would have to spread out more than 10 times its observed width in the supposed age of the galaxy. This, together with the extraordinary length in the circularity centered on the observer, as if its redshift distance argues for intrinsic redshift and much more near distances for a chain. The redshift of the two bright Able clusters at either end of the straight lines connecting Perseus A and NGC 891 in Figure 610 are typical redshifts for galaxies in the Perseus-Pisces filament. To the southwest of NGC 891 is a bright cluster of Z equals 0.016, again, a characteristic redshift for the filament. In other words, the chain of galaxies recommences after a gap as if the counter ejection from NGC 891 had been directed at a somewhat different angle. This is reminiscent of the possible configuration of clusters around NGC 5253 discussed in the two sections earlier. In order to fully appreciate the involvement of NGC 891 with the Perseus-Pisces filament, one should consult the computer plot of these wiki catalog galaxies by R. Giovanelli, as shown here in Figure 611. It can be seen here that both sides of the long filament deviate from their course on the west side and point towards, and on the east side, and essentially join at the position of NGC 891. It will be later seen in a discussion of galaxies alignments that most of the bright stars in the galaxy in the sky have broken lines and higher redshifts of the galaxies originating from them. So here we have our Ricardo. Giovanelli composed a picture of galaxies in the Zwicky catalog. It shows the Perseus-Pisces filament stretching nearly 1/4 away around the sky. The position of NGC 891 is added with a plus sign. All right. Testing the ejecting spiral, NGC 1097. The barred spiral is a very bright Seyfert hotspot starburst galaxy with the longest straight optical jets known. To test the hypothesis of ejection of cluster in the region around NGC 1097 was examined, and the catalog of was examined in a Able catalog of galaxy clusters. The upper right corner in Figure 612 shows that the 4 optical jets in NGC 1097 are extended outwards, and they include within their injection angles Able clusters in the vicinity that are of a brighter magnitude than 17. That these directions really represent the ejections of intrinsically high redshifted objects is attested to by the color plate in 2.7, and all the studies of NGC 1097 referred to in Chapter 2. The northeast direction, just where the optical jets are the strongest, the excess number of quasars is the greatest. And the southwest direction, where the optical jets were weaker, the excess number of quasars were the next greatest. It turns out that the number of clusters is correlated to the number with the strength of the jet. In the process of examining NGC 1097's field, we, however, noticed a number of galaxies clustered in the southwest. I had forgotten about the large nearby Fornax cluster. Fornax A, the twin of Virgo A. As Figure 612 shows, the brightest galaxy in this 28 by 24 degree region of the sky is NGC 1291 at BT equaling 9.4 magnitude in a redshift of with a redshift velocity of 738 kilometers a second. This is the center of what turns out to be almost the exact duplicate of the Virgo cluster in roughly the opposite quadrant of the sky. The resemblance is uncanny. For example, the brightest galaxy in the center of the Virgo cluster, M29, has a brightness of 9.3 and a redshift velocity of 822 kilometers a second. Almost an exact match for NGC 1291. In the Fornax cluster, there is a very bright, very strong radio galaxy, 4A, about 4 degrees away from the central galaxy. In the Virgo cluster, we have M87, only about 4 degrees away from NGC 4472. These are the very close match with a brightness of 9.6 magnitude and a redshift velocity of 1713 kilometers a second. For 4A has a brightness of 9.6 magnitude and a redshift velocity of 1136 kilometers a second. From 4A, there are 2 radio galaxies in a straight line, suggesting an ejection direction. The inner radio jets of 4A are aligned at PA equals 126 plus or minus 14 degrees. But at the major axis of the spheroid, we know, as well as the unresolved optic knots, which are aligned along it, are at 59 plus or minus 1 degrees. This is the alignment of 2 radio galaxies toward 4A, which is 61 plus or minus 1 degree, and it would seem to delineate the outer ejection locus of the major galaxy line of galaxies aligned for 4A. All right. But now notice the plus sign in figure 612, which represents the Abel cluster of galaxies. They fall right down the spine of the Fornax cluster. This is the same distribution of clusters we found in the Virgo cluster, and it cannot represent an accidental projection of background objects. These bright, quote, galaxy clusters must belong to the nearby great cluster Virgo and Fornax. In order to emphasize the amazing similarity of these 2 clusters, I superposed in figure 613 the X-ray outline of the Virgo cluster from figure 515 on the Fornax cluster. The scale of the sky is about the same, but I have mirrored the image outline of the Virgo X-rays. It is as if we were looking at 2 identical clusters from a midway point between them. Interesting. The reader will have to follow the implications further, but I will add the doubling and twinning cosmic objects seen that seems, in my experience, to be common. The double twinning of cosmic objects, yeah. Okay, so we got our diagram here. The diagram of the Fornax cluster is shown in figure 612, but now with the X-ray outline of the Virgo cluster in figure 55 drawn in, or 515. The Virgo cluster outline has a mirror image and is rotated slightly, but it is identical in scale. The lower circle represents the position of M49 in the Virgo cluster, and the upper circle represents the position in Virgo A. Of course, I have tried from the ROSAT survey to map the extended X-ray emissions from Fornax as it was done in Virgo, but there are satellite scans which are corrupted as they pass near the Fornax cluster, so the rest of the predictions are made from figure 613 will be an exciting possibility only from the next generation, only from the next generation, all sky X-ray survey instruments. All right, the Hubble diagram for galaxy clusters. The immediate objection to nearby clusters of galaxies is that the clusters are supposed to be composed of galaxies, just like those in our outer cluster in the Virgo cluster. How do we know this? Because they have large redshifts, which place them at large distances and therefore require the galaxies to be luminous and large. But the whole thrust of evidence so far in this book has been to show that the extragalactic redshifts do not generally mean velocity, and the younger objects with a higher intrinsic redshifts are closer in distance with lower luminosities. Are many fainter galaxy clusters composed of young objects? Therefore, we tackle that question. Let us test the one observational relation which the clusters must pass if they are at conventional distances. Namely, do they define the Hubble relation? Figure 614 shows that 14 clusters with redshifts from the large region in the north of Centaurus A, pictured in 6.7, The best fitting Hubble relation is shown by the dashed lines. The spread from this line is enormous. The classical dispersion around the Hubble relation is supposedly distant clusters is only that of a few tenths of a magnitude. The total range in figure 614 is at the given redshift, in contrast, is about 4 magnitudes. That would require the luminosity of the characteristic galaxy in a cluster to range by over a factor of 40. Of course, the magnitudes of which are used in the classical definitions of Hubble slopes would have a whole series of corrections made to them, whereas the magnitudes listed for the Abel clusters are simply estimates made from a Schmidt telescope photographs. The corrections which can be made to these photographic estimates, however, are very small compared to the range of the deviation from the Hubble line in figure 614. Therefore, we must conclude that the apparent magnitudes of these galaxies in the clusters correlate very poorly with their redshift. Measured in another way, at a fainter 16th apparent magnitude in figure 614, the brightest redshift clusters exceed by about 30,000 kilometers a second. Clusters exceed by about 30,000 kilometers a second, and the redshift which a cluster with the average luminosity galaxies should have. The Hubble line is supposed to have a velocity dispersion of about 50 kilometers a second, even though the adventuresome observers have only claimed peculiar velocities of the clusters between 1,000 and 2,000 kilometers a second. The upshot is that although the clusters with fainter galaxies tend to have higher redshift, there is no redshift apparent magnitude relation for these clusters like that which is claimed to demonstrate for the redshift distance relation. In Chapter 9, we will attempt to make a more quantitative analysis on the situation, but we will now like to go gather some more examples of the shocking results involving nearby clustered galaxies. We got our Hubble line here, and I think all these dots here are supposed to be intersected by your boy Hubble line, but that doesn't appear to be happening. 614. All Abel clusters with the measured redshift from the large area north of Centaurus A are shown in figure 6.7. The best fitting Hubble line is the dashed line. The maximum deviation from this line is about 30,000 kilometers a second. Okay. All right, of course, the magnitudes which are used in the classical determinations of the, oops, wait, I think I read all that already. We're on this part. NGC 4319 and Mark 205, a very active system. The distributed spiral galaxies, NGC 4319, was first noticed because of the high bright Seyfert/quasar Markarian 205. It fell only 40 arc seconds away from it. Of course, the chance of this happening by accident was negligible, but conventional astronomers were certain it was an accident because the redshifts of the two objects differed by about 20,000 kilometers a second. When the luminous connection was discovered between these two, of course, the great fight erupted, with the conventional side saying that the connection did not exist. See quasars, redshifts, and controversies. But the common sense point, which no one ever said much about, was in fact that the galaxy NGC 4319 was obviously in the process of being destroyed. One might argue that the close proximity of the very active Mark 205 was responsible, but even more plausible reason was the apparent fact that the two spiral arms of NGC 4319 were coming off at their roots. There apparently had been a rather violent and recent explosion at the center of the galaxy. Dude, I love how they're like CSI investigators looking through a telescope. They're like, this is what the killer must have, Anyway,
well, you know what happened was everything exploded all the way over here, and then that caused with the thing that we're seeing. It's perfect. It makes perfect sense.
Like, oh yeah, the center of the galaxy exploded, severing its galactic arms. Like, what? Yeah, okay. All right. This was supported by the fact that most of the gas expected in the galaxy was missing. Oh well, you know what they say, Shane. When there's missing gas, there's an explosion.
Well, we know what type of gas because the stellar spectroscopy and its woefully unconfirmed scientific status, where we just look up and speculate. So that's how we know.
Dude, when they know what type of gas there wasn't.
Ridiculous. All of this.
Okay. The arguments for Mark 205 has been ejected from the argument that Mark 205 has been ejected from NGC 4319 have been detailed in my previous book. The account for how Jack Sluntic measured the only good radio map of the system at a very large array in New Mexico and demonstrated the surprising fact that the spiral was also ejecting radio material has also been recounted. But what is not discussed was that the fact that these ejected radio lobes were centered on some rather ordinary looking galaxy of a considerably higher redshift. We agree that these look like radio galaxies in the cluster. I said to Jack, someday we should have to face the fact that these objects were also ejected out of NGC 4319. He just looked appalled and shook his head.
We'll never face that, Jack. Don't you worry.
I'm never going to face that, bro. That's what he said. He was like, that's your quest, bro. That's not mine. So now it's come the time I have to point out that the patch of radio emissions in figure 615 lead from the center of NGC 4319 out in the northeast direction to the two radio lobes unmistakably centered at the moderately faint galaxies. Two redshift, dude, now we got to face it, dude. He was right. The redshift of the stronger radio galaxy is Z.343. And there are obvious fainter galaxies which form a cluster. In the counter direction, the radio lobe encircles the fainter galaxy, which has an apparent tail of radio and X-ray emissions coming off to the southeast. The latter represents the significant connection between the classical double lobe radio ejections and the younger, higher redshift X-ray objects, which are shown to be ejected earlier in the chapters of this book. Further out along the line of X-ray material, which leads from Mark 205 to a redshift value of 0.464, the quasar is a strong X-ray source, marked CL. In figure 1.7, also the visible plate in 1.7, the source has been identified as a cluster of galaxies with a redshift value of 0.240 by John Stoke and others. What this means is that we have two clusters of different redshifts situated along lines of an ejection from the Seyfert Mark 205, and in the interacting disturbed the spiral of NGC 4319. Took it clean out, dude. He just reversed the whole trajectory. The galaxy just
Man, this thing is like a
just
super excited super nerd writing fan fiction that gets him like excited the more he thinks about it, and then he invents like a new land. Oh, and then a new race to live in the new land. Oh, and then they have this new type of magic, and then that's what all of this is. It's just assumption upon nothing upon fairy wish, dude. It's crazy.
I mean, dude, but clearly
Like-
though, you're just not willing to face the fact that galaxy sniped the other one.
It's like, and you can tell that I'm right because, you know, the X-ray material, which no one can see, which we have to filter through telescopes, and ultra spectroscopy actually confirms it in the way that its spiral arm articulates off to the side. And it's, you know, it's like, what? That confirms it? Okay. All right.
Over it, and then like you got to realize too, it's like the timeline that would like confirm all this would be like over millions and billions of years. Well, I actually,
you know, simultaneously, you know, it must have happened 60 billion years ago. The thing that I'm looking at now, that's why it's there.
yeah. So he would argue for millions of years, not billions. My bad. So he's a millions of years lad, but still, like the timeline on this is like it's like, you know, this is all, you know, in his head, as you said. But like you see how it's like conflicting with what they've established and what they know, right? Like they go as far as to make like 9 assumptions to determine how the thing that's inside of the jet stream can't be inside of it. It has to be behind it. It's like they're just as egregious. And they're like, and because this guy like knows the significance and is accredited, he's like, you know, dangerous to them. It's crazy. They won't let him play. He just wants to play. And they're like, no, you're not following our rule book. All right, so these are the kinds of cluster galaxies which have been shown in the earlier sections of the chapter to be associated with low redshift ejecting galaxies. So NGC 4319 and Mark 205, where there is direct evidence for ejection of the cluster of the galaxies with a shift value of 343 and 240 or 0.240 from the active galaxy represents another example supporting the case of NGC 5548, since NGC 4319 also has probably ejected the Mark 205, which in turn ejected the quasar, which is shown in chapter 1, is perhaps an understandable that NGC 4319 looks somewhat exhausted. Dude, it looks tired out there in the sky, bro. Needs a little nappy nap. Other candidates for the ejected clusters. No attempt can be made to complete, or no attempt can be made here to be complete because there are so many instances of high redshifted galaxy clusters with evidence for ejection origins from lower redshifted active galaxies, but few cases will be cited to give the flavor of the kind of evidence which could be followed up with further observations. In figure 1.1, in the first chapter of this book, NGC 4258 shows the typical extended X-ray source of the northwest end of its main disk, an X-ray cluster of galaxies. At the source, that source contains a line of moderately faint galaxies, which is somewhat in the same direction of H2. In the directions H2 regions at the end of that galaxy. Note that they are aligned on the mark of non-equilibrium configuration because their conventional lifetime is even small, peculiar velocities would disrupt the line. Okay. NGC 4151 shows the conspicuous straight line of fainter galaxies to the west of its nuclear region in figure 316. This line of galaxies points closely back to a very active companion Seyfert galaxy, NGC 4156. From what we are now seeing, this does not look so much like a coincidence. The five redshifts measured in the line from left to right are 0.060, 0.160, 0.158, 0.16, 0.056, and or 0.24. The redshifts are in agreement and indicate that the cluster-like association and the ones in disagreement represent anomalous redshift because they are obviously part of the same linear feature. Also note the agreement of redshifts was previously quantized peaks. X-ray maps on the edge of the galaxies of NGC 4565 and NGC 5907 show the X-ray clusters on the galaxy of the nucleus, which show evidence of the elongation back toward the nucleus. The X-ray galaxy cluster Able 85 is only 41 arc minutes to the north of NGC 217, and it's 10 to 15 degrees off the alignment with the major axis and extended towards NGC 217. Extensive studies of active galaxies like starbursters, NGC 253 and NGC 3079, show X-ray emissions extending out into the halo regions, especially along the minor axis directions. For NGC 253, some of this emission is identified with faint galaxy clusters. I would take this as a very strong evidence for the cluster of small intrinsically shifted galaxies to originate by ejection along with other higher redshifted material like the quasars and the BL-LAC objects. On Palomar and UK Schmidt survey plates, I have seen the occasional galaxies with streamers of faint galaxies extending away from them. In the ESO, there is a definitive picture of quasars and cluster galaxies emerging from a fountain from the larger and lower redshift galaxies, There are many examples of the clusters following provocatively close to the lower redshifted galaxies could enumerate, but of course, what should be done is to cross-correlate the list of two kinds of objects by computer analysis and then investigate the critical individual cases in detail. All right. Who can consider the drastic change? In 1993, I was very excited because this was the main staggering change in concept, but one day it seemed inescapably to require by observation, but one day that seemed inescapably required by the observations. After all, look at figure 6.1b, 6.2, 6.7, and 6.13 just by themselves. But at the time, the best scientist I had personally worked with and value as a personal friend visited the Garking Institute, Fred Hoyle, and Margaret and Jeff Burbage and Janet Narlikar. It was nice to have them there because I felt like it bolstered my unpaid visitor status at the Max Planck Institute for Astrophysics. With great zest, I laid out before them what I had discovered about the galaxy clusters, and they were horrified. Jeff said that the redshift apparent magnitude relation, which was accepted for the galaxy clusters, meant that they had to be at their redshifted distances. He just immediately started cogdissing out. He's like, ARP's like, your conclusions, my premise, bro. Fred said that my embracing such an obviously crazy result would undermine the credibility of our attack on the Big Bang. He was visibly angry. How could I do this to a person who had me thrilled beyond expression by coming up from Caltech campus to my office at Santa Barbara Street to see my original observations in the late 60s? Perhaps I was hoping for some more support and advice on strategy, but it was clear that the people I had admired the most thought I was ridiculous. Though, through my disappointment, I had to admit they were completely right. The results and everyone remotely connected with it would be ridiculed mercilessly. Struggling with feelings of shame and apprehension at the time, I felt that the results were correct and I had to think of it in a way to communicate them. My first thought was to send them to the Indian Journal of Astronomy and Astrophysics. It would be almost certain that they would not be read there by any of the establishment bulldozers. The results would be referenceable, and at least they would not be lost. That reminded me that for a few years before I had published in the journal another unbelievable result of alignments of high faint redshift galaxies across almost the closest and bright low redshift spirals. With a small jolt, I realized that was very close to what I was finding now with the galaxy clusters. Well, I had escaped ruin before, and with the new results were a nice support to the previous ones. I had started with a letter of submission when I thought about the important results on the injected X-ray quasar that were in a unique position to be launched towards publication. What if my access to the data was shut off? At that point, I put down my pencil and said, well, maybe it won't hurt to postpone submitting the galaxy cluster paper for a while. Dang, he was afraid he would get hella censored. Straight postponed it. All right. So here it is for the first time in this chapter. Later in this chapter, I will indicate how the earlier publication on my galaxy alignments supports the new cluster results. Complete sample of X-ray clusters. As soon as the systemic X-ray observation of the night sky had begun. It was discovered by many it discovered many able clusters were strong sources of high energy radiation. We will argue that this marks them as young, active entities, but as practical matter enables X-ray observations to search systematically for galaxy clusters. As in the case of the quasar, the X-ray survey enables the class of the galaxy cluster to efficiently be picked out of the large mass of background objects. In 1994, a complete survey of X-ray clusters over large regions of the southern hemisphere were published. As a figure 616 shows the striking concentration of X-ray clusters in the region, and the two brightest galaxies in this region are at the centers of this concentration. They turn out to be Centaurus A and M83, just as the galaxies we associated within the cataloged able clusters in the beginning of this chapter. Figure 6.7. This most recent survey then furnishes an independent and striking confirmation of those original results. The most amazing thing about this investigation is perhaps the most obvious non-random distribution of the X-ray clusters in this region of the sky and the failure of the investigators to comment on it. Perhaps the next most amazing aspect of this is that the largest grouping of the brightest X-ray clusters in the whole region conspicuously coincide with the brightest galaxies in the region, but went unremarked. Why would the brightest X-ray cluster coincide with the brightest galaxies in the Centaurus A group if they were unrelated background objects? The remaining X-ray clusters in this area, though less bright, form two distinct strings, the end of which also coincide somewhat less bright, but still major galaxies, NGC 3223 and NGC 3521. One valuable aspect of this study, however, is that the investigators were obviously not previously biased in favor of finding galaxy clusters associated with nearby galaxies. Another sensational result, which was not noted, was that the X-ray cluster in the surveyed area had an enormous redshift peak of 0.06, figure 617. The reason why this is such a key result is that the analysis of the quasar and AGN redshifts show that the first quantization peak at about 0.061. See the following chapter. Pencil beam surveys of the field galaxies show this peak, but the active quasar-like objects show it much more strongly. The presence of this peak with such great X-ray strength galaxy clusters marks them as young, intrinsically redshifted objects. Blue galaxies in high redshift clusters. A few clusters of galaxies with redshifts appreciably above the limit of the Able cluster have been investigated in detail. 3 with the redshifts of a value of 0.41, 0.42, and 0.54 have been described by R.J. Lavery, M.J. Pierce, and McClure. They are outstandingly peculiar. They do not look anything like our galaxy or the Virgo cluster galaxies. They are rich in blue and ultraviolet light and have increased fractions of emission lines, galaxies, and distributed morphologies. In short, they are young galaxies, just in the kind that we have found empirically to have increasingly amounts of intrinsic redshift. When this Butcher-Ohmler effect, as it is now called, was first discovered for the clusters that are greater than a redshift value of 0.2, it was a great shock to the orthodox theory which expected these standard candles, the standard candle, to remain constant, but their properties were too large in redshift. There was no alternative for the Big Bang adherents but to accept that the very short distances from the universe changed drastically. The very short distances from us, the universe changed drastically. This disaster was papered over by attributing it to evolution. Classic. But no one faced the fact that the whole Big Bang solution of the general relativistic field equations rested on the assumption that the universe was homogeneous and isotropic. Dude, that's so unfortunate when they forget to solve the nonlinear field equations. You have to assume the input boundary conditions, or the input conditions and the boundary conditions. For the empirical age redshift law, which have been developing, however, the observed behaviors of the young clusters is what we would expect. The galaxies in them are low luminosity and high redshift when first born from the nearby older galaxies. At a greater distance, they are too faint to be seen, so these clusters are all nearby, even if they exist at more distant examples. A clinching observation is that of so many of these galaxy clusters are strong sources of hard X-rays. Galaxy clusters are supposed to be ensembles of old objects. How can they irradiate so much energy for so long? The canonical explanation of this is cooling flows. Big old galaxies at the center of the clusters eject hot gas which emits X-rays as it cools off into the mass center, or into the center, falls into the mass center. But this hypothesis is based on the assumption that the high energy radiation is in equilibrium over the supposed 15 billion years of the clusters, an assumption about which is the most polite thing one can say about it is unwarranted. Agreed. In any case, after the innumerable publications of extolling cooling flows, it turns out they won't work. Oh no. Cooling flows in galaxy clusters. A typical cooling flow has at least 100 solar masses per year. Over 1 billion years, this would entail 100 billion solar masses. Where is it all hiding? One cannot hide this much star formation from the optical observations. The gas cannot be warmed molecular gas because it would have been observed in the millimeter wavelength of the emission lines. The gas cannot be cold molecular gas because then the same wavelengths would reveal the absorption lines. The last refuge is low mass star formations, but such stars would show strong absorption bands in near infrared. Dang, spectroscopy gets him again. Some cooling flow theorists have admitted that the hypothesized mechanism leads to catastrophe because it requires too much mass to be dumped into the central galaxy. They have tried to turn the failure into fortune by arguing that the mass is thrown out again by the jets and ejections. But this just raises a whole new set of problems of smoothness and lifetimes and goes against the observations of the clusters that have jets without any X-ray gas. Oh, foiled again. Clusters of young objects. The fact that these galaxy cluster characteristics emit high-energy X-rays mark them as young, just as the newly ejected quasars in the first few chapters are marked as young by, among other things, their rapid rate of X-ray production. And of course, we have seen in the beginning of this chapter the X-ray cluster ejected from NGC 5548 with a Z value of 0.29, which is about the luminosity of the ejected quasar divided into 16 pieces. The spectrum of an individual galaxy in one of these clusters usually reveals the composite of absorption lines from the stars that are contained in it. As we discussed in Chapter 4, the lines can tell us that the stars are older than a billion or so years, but they cannot tell us whether they are as old as 15 billion years, which is required by the Big Bang. As calculated previously, they can only go plus or minus a billion. They can't go plus or minus 14 billion. It's fair. As calculated previously, a galaxy of matter created only 2 billion years later than our own would have an intrinsic redshift value of about 0.1. But the oldest stars would only be 12% younger, and this would not be readily detectable in the composite spectrum. As we have pointed out in this chapter, however, when the galaxy cluster redshifts approach 0.2, the constituent galaxies start turning very blue and showing non-equilibrium shapes, a sure sign of young galaxies. That's how you know you got a young buck galaxy in your sight, when it's showing non-equilibrium shapes. and it's very blue. There have never been a careful discussion or detailed sequence of comparisons of individual galaxies to check the assumption of faint galaxies of fuzzy smudges of light where they were the same nearby great clusters, only seen at great distances. One could see a blatant difference in comparing the X-ray properties of the fainter to the great clusters like the Virgo cluster and A1367. A continuation of the Virgo cluster in the northward in the supergalactic plane. Because of the latter clusters, the individual large galaxies were X-ray sources, and a vast number of much smaller X-ray clusters. The whole group of objects was embedded in a diffuse X-ray emitting medium. The latter was a much different cluster, was a much different kind of cluster. Moreover, the cluster of the Coma cluster did not even contain galaxies that looked like the giant SBs and SCs in the Virgo. They were essentially just the star piles called E for elliptical galaxies. The continuing assumption that the faint little fuzzy spots in the clusters of vastly smaller angular extent are the same kind of galaxies populated in the local supercluster seem not terribly good judgment in view of all the evidence for anomalous redshifts. The Fornax cluster revisited. Black objects. We're just going to simplify that. All right. In the final synthesis of what we have been talking about so far, quasars, black objects, and clusters of galaxies, we return to the Fornax cluster galaxy. We take the same plot of the bright Fornax galaxy and a bright Able cluster as previously shown, and we will now plot the positions of all known black objects in this large area of the sky. The first point of interest of the two of them is the fall in the northeast ejection cone from NGC 1097, a new black object itself as discovered in the ROSAT survey scans by ARP and Apparel, then falls in the southwest ejection cone. There seems to be a clear ejection of the quasars, blacks, and galaxies clusters from this very bright and very active Seyfert galaxy with a striking optical jet. Two other black objects in this field fall close to the populated portion of the Fornax cluster. One of them we have discussed before in Chapter 2 as falling only 12 arc minutes from the spectacular barred spiral NGC 1365. The observers who measured the neutral hydrogen in the galaxy mentioned that it was extended in the direction of the center of the Fornax cluster. If they had meant NGC 1291, that would be the position of an angle of 212 degrees, but at position angle 203 degrees is the black object, which is much, much closer. It would be reasonable to conclude that the hydrogen in NGC 1365 had been entrained by the outward passage of the black object. The fifth black of the redshift is 165, falls close to the major concentration of galaxies and Able clusters in the Fornax cluster. It is clear from figure 618 that the Fornax cluster represents a hierarchy of redshifts. The largest galaxy in the cluster and has the lowest and the oldest has the lowest redshifts. Successive generations of that's hilarious, dude. They got it completely backwards. Isn't that par for the course? They just inverted it. It's pointing at us, and they're like, "It's going away from us, guys." All right. Let's see here. Successive generations of galaxies and smaller, increasingly young and active galaxies climb to the higher intrinsic redshifts and steps. The younger galaxies emerge in opposite ejection directions, and with some rotation, give, as in Virgo, a small overall S for the spiral pattern for their cluster shape. The arrangement of the known quasars within the ejection cone of NGC 1097 and the occurrence of the black objects in the Able clusters further out in the cone suggests the possibility of a very important generalization of the properties of ejected objects. The suggestion of the higher redshift quasars are initially ejected objects and that they travel outward, their redshifts decay and their luminosities increase as their particle mass increases. By the time that they reach a degree so far from their galaxy of origin that they have evolved into a bright apparent magnitude of z equals 0.3. The range in which they were liable to emit the energy burst, which transforms them into a short-lived black phase. Perhaps at the time they can fission into a number of smaller parts and become an Able cluster, which go on to evolving into lower redshifts and increasing luminosities for their individual galaxies. A schematic representation of this evolution is pictured in 9.3 in Chapter 9. In any event, the objects as they are plotted in Figure 6.18 establish at a glance that they are all physically related, and that some of the smaller, more active objects have increasingly amounts of intrinsic redshifts. It is a picture where one has to either show that the plotted objects are not the brightest objects in their class, or bite the bullet and accept the observational result. When looking at this picture, no amount of advanced academic education can substitute for good judgment. In fact, it would be undoubtedly an impedant. Yeah. Black objects as the progenitors of galaxy clusters. By now, it is observationally obvious that there are an innate connection between black objects and galaxy clusters. Since the black objects are redshifted intermediately between quasars and galaxy clusters, in an evolutionary interpretation of the redshift, the black objects would have to be the progenitors of the galaxy clusters. The key question is whether there are any observations which would validate this inference. The interesting thing about the empirical observations is that they tell us that the blacks break up, and they tell us how they do it. Just as in the ubiquitous ejections that accompany the formations of the young stars in our galaxy, the blacks eject material in the opposite direction. Apparently, they eject a lot of it and eventually ages into smaller, somewhat higher redshifted companion galaxies that form into clusters of smaller redshifted objects. This result was the foreordained. When one considers the blacks were shown by John Stokes and the collaborators to occur in cluster environments. Since the blacks are associated with nearby galaxies, the clusters must also be. For example, black type quasars, as shown in Figure 1, are to be linked to low redshifted galaxies. Stock also has shown that the quasars belong to a cluster of galaxies. See Figure 8.11 through 8.13 for a cluster quasar in process of evolving into cluster galaxies. We're almost done, lads. In the great galaxy clusters, the Virgo and Fornax. The Fornax cluster is not well known because it is in the southern hemisphere and it is not studied as intensively as the Virgo cluster. But for the redshifts, which are, okay. But for the redshifts which are known, it is fascinating to note that there are similarities with the Virgo pattern, or patterns with Virgo. As noted previously, the Fornax cluster has a large central galaxy and a strong radio galaxy. Forn A show the same pattern as the Virgo cluster. Virgo cluster with M49 and Virgo A. In the Fornax, the two strong galaxies extend in a line that form Forn A as M86 and M84 extend away from it in Virgo A. So like they got the same thing, but just in the southern hemisphere going in the opposite direction. So like, Shane, what's that word you're looking for when you mirror something or whatever? I think that's like even their shift values are similar. Again, the Fornax cluster as the Virgo galaxy cluster for the radio galaxies, and the spiral galaxies have systematically higher redshifts. It is particularly interesting to note that the luminosity class I spiral NGC 1365 is plus 824 kilometers a second with respect to the central Fornax galaxy NGC 1291. The four SI spiral that are members of the Virgo cluster are 582, 642, 824, and 1079 kilometers a second, respectively, for their redshift values of the brightest galaxies in the cluster of M49. So it is clear that the SI spirals, that the SI spirals are classes of galaxies with well-established intrinsic redshifts. There is also a concentration of quasars in the Fornax region. We have seen both Fornax and Virgo. We have both seen in Fornax and Virgo how able clusters outline the S shape down the spine of the cluster. We have also seen how the black objects fall along the distribution in Fornax. It suggests that we look at the distribution of the black objects in Virgo, and when we do, we find too little below and a few degrees to either side of M49. Their redshifts are 0.136 and 0.150, a good match for the redshifts in the 1.65 redshift black objects in Fornax. So yeah, pretty close. These two clusters are such a good match in details, including the hierarchy of intrinsic redshifts, that I am tempted to say that there is a creator. So I would not presume to attribute anthropomorphic properties to it. And might expect to hear things like, "Look, you dummies, I showed you that the Virgo cluster, and all you did was believe that what I was show you another one just like it. And if you still don't believe it, well, let's just forget the whole thing." Yeah. All right, galaxy alignments. If anyone plots galaxies in the sky as a function of their redshifts, it is clear that they form long, irregular strings. The most amazing property of these linear distributions is that the brightest, lowest redshift galaxies fall in the region in the middle of each of these strings. The situation is shown in figure 619 for the longest string, the Perseus-Pisces filament that I have shown. There is a string of about 3,100 to 5,100 kilometers a second galaxies that stretch more than 40 degrees across the northern sky. Right in the center of it situated a giant SB spiral M81, the next nearest galaxy, major galaxy to our own local group, having only a redshift of 100 kilometers a second. Just to the west of M81 is a companion SC NGC 2403 with its own shorter string of higher redshift galaxies. Then to the south, we see other strings. Then to the south, we see two other strings of galaxies, best outlined to be 4,200 and 5,200 kilometers a second in redshift range. Here in figure 620 shows that each of these, the latter strings, has the large, low redshift SBs at its center. In the Indian Journal of Astrophysics and Astronomy, I was able to investigate 20 of the brightest apparent magnitude spiral galaxies north of a declination 0. Of the 14 of which were uncrowded by nearby bright galaxies, of a total of 13 had well-remarked lines and concentrations of fainter, brighter redshifted galaxies. It is embarrassing to have to report that the chance of this occurring by accident is less than about 1 in 10 billion to 1,000 billion. All right. To 1 in 10 billion to 1 in 1,000 billion. The calculation of this made at the request of the referee, who afterwards appealed, still not wanting to believe the plots of the galaxies cataloged. Rather than repeat all the plots, I will just show one more figure, 621. All of the galaxies listed in a complete revised Shapley Ames catalog by Sandage and Tamman are plotted here. There happens to be a scarcity in the particular region, so the bent alignment of galaxies is very conspicuous. Again, just in the middle of the string is situated to the brightest, lowest redshift and galaxy in the whole area, again in SB. The two galaxies in the string are SIs, a particularly young kind of spiral, which was shown previously to have a particularly conspicuous excess redshift. This brings up an important point that in cases of the original brightest 20 brightest spirals, investigations of these kinds of galaxies in the strings turned up to be an outstanding number of SIs, distributed, irregular, double, peculiar, and active galaxies as Markarian and Seyfert galaxies. This is a clear addition. This clear addition confirms the non-accidental nature of the strings and points strongly to the conclusion that the redshifts of aligned galaxies are intrinsic and caused by their young age. Alignment of quasars, black objects, and galaxy clusters. Without going into ritual modes, without going into the ritual models and detailed calculations of science, we can induce quite a bit of misunderstanding just by noting the empirical relation that the data we have discussed thus far. 1. Objects appear young and are aligned at either side of eruptive objects. This implies that ejections of protogalaxies. The youngest objects appear to have highest redshifts and implies the intrinsic redshift decreases as the object ages. The distance from the ejecting central objects increases. The quasar increases in brightness and decreases in redshift. This implies that the ejected object evolve as they travel outward. At about z.3, and about 400 kpc. Is that what is that? From the parent galaxy, parsecs. From the parent galaxy, is the quasar appears to be very bright in optical and X-ray luminosity. This implies that there is a transition to black objects. All right. We got our diagrams here. All galaxies with redshifts greater than 1,300 kilometers a second from the revised Shapley Ames catalog are plotted. The bottom panel appends their redshifts in hundreds of kilometers a second. The central brightest galaxy in the SB morphological type crosses the later type spirals and large crosses in their SI types. Few black objects are observed, implying their phase is short-lived. 6. Clusters of galaxies, many of which are strong X-ray sources, tend to appear comparable distances to blacks from black objects from their parent galaxies. This suggests the clusters may be a result of breaking up of a black object. Clusters of galaxies in the range of z.4 to z.2 contain blue active galaxies. It is implied that they continue to evolve to higher luminosities and lower redshifts. 8. Able clusters from 0.01 to 0.2 lie along the ejection lines of the galaxies Centaurus A. Presumably, they are evolved products of their ejections. 9. The string of galaxies which are aligned through the brightest nearby stars have a redshift of 0.1 to 0.2, or 0.01 to 0.02. Presumably, they have the last evolutionary stage of the ejected protogalaxies before they become slightly higher redshift companions of the original ejecting galaxies. The connection between these dots of facts, which reveals the whole picture, seems to be that the newly created high redshift materials is ejected in opposite directions from active galaxies. The material evolves into high redshift quasars and then progressively lower redshift objects, and finally into normal galaxies. This summary conclusion is elucidated further in the theory in chapter 9, but here is an example of the working hypothesis. It could be used to deduce what type of physical processes are required to produce the observed effects, i.e., which theory out of the infinite number of possible theories is the closest to reality. as a working hypothesis, it stands to ready to amend that anytime better observations become available. For example, it is not clear whether the large amount of newly created material will evolve in the same way that it does for a small amount. It is possible that new material will be trapped in the interior of the originating galaxy, condensed, and then be ejected out into a later event, which has a more evolved state. In my opinion, the above is almost exactly the opposite of what the current academic science works. Regardless of how scientists think they do it, they start with a theory. Actually worse, a simplistic and counter-indicated assumption that the extragalactic redshifts only mean velocity. Then they only accept observations which can be interpreted in terms of that assumption. Well said. This is why I felt it was so important to go as far as possible with empirical relations and conclusions. This is why it is so important to discard any working hypothesis if it's contradicted by observation, even if there are no alternative hypothesis to replace it. As unpleasant as it is, one must be able to live with that uncertainty. Or, as many people say, they do not believe it is possible to prove whether a theory only to disprove it. And on that, we're gonna wrap it up. Any thoughts, lads?
I have a quick comment.
You got it, Lily.
Hey, yeah, I was thinking, I have a really active imagination, and I should have become an astrophysicist because I could have given way more colorful explanations for everything that we observe in the skies, honestly. So, yeah, that's what I was gonna say.
Dude, that would be so awesome if you were in charge of writing our cosmology, Lily.
I know, I have a really colorful idea of everything that I see and interpret, Yeah.
Yeah. Yeah. All right, lads and ladettes, we're gonna go ahead and wrap up for this roundtable. Join us on Friday for the Twitter community space, and then Sunday on Glowbusters, where Shane's going to be doing his presentation on the celestial and terrestrial spheres, tying it all together on his 3-part series. So thanks, everyone. See